The quantum mechanical model of the atom, the wave nature of light. In this tutorial, we will be going over the wave nature of light, amplitude, wavelength, and frequency, and example problems involving speed of light, frequency, and wavelength. The wave nature of light. Energy in the form of light is classified as electromagnetic radiation. Electromagnetic radiation can be described as a wave. Waves are characterized in three ways: by amplitude, wavelength, and frequency. The amplitude of the wave is the vertical height of a crest or depth of a trough. The intensity of light is directly proportional to the amplitude of the wave. So we can see in this chart over to the right two examples of low amplitude and then two examples of high amplitude. The wavelength is the distance between two repeating points on a sine wave. So if we were to look at the wavelength here, we'd be looking at the distance, let's say from the bottom of this trough to the bottom of this trough, so this distance right here, or from the top of this crest to the top of this crest. So this distance right here. That is what we define as wavelength. The frequency is the number of wave crests that pass a fixed point in 1 second. So in this chart, we can see the difference between low frequency and high frequency in terms of low amplitude, and low frequency and high frequency in terms of higher amplitude. The wave nature of light can be represented by the formula C equals nu times lambda, where C equals the speed of light in a vacuum with a quantity of 2.998 times 10 to the 8th, and the unit is meters per 1 second. Nu is our frequency of radiation, where the units can either be per second, that's what this s to the negative 1 means per second, or hertz. And then finally, lambda, which means wavelength, where the unit here is the nanometer, represented as nm. This relationship is included in the atomic structure section of the College Board AP Chemistry reference tables, so make sure that you know where that is located. Let's do some example problems. Calculate the frequency of radiation that has a wavelength of 955 micrometers. So remember that this symbol right here means micro. So the first thing that I'm going to do is write my formula. Speed of light is equal to the frequency times wavelength. Now I'm solving for frequency here. So what I'm going to do is I'm going to rearrange my formula so I've isolated that variable. So if I isolate it, so it's frequency is equal to speed of light over wavelength. Now the key thing to realize here when you look at speed of light is that speed of light is in the units of meters per second, and we have a wavelength of 955 micrometers. So the first thing that I'm going to do is get rid of the micrometers and convert this into meters. So over here off to the side, I'm going to say 955 micrometers, multiplication sign and a line, and I know that there is 1 times 10 to the 6th micrometers in 1 meter equals, micrometers cancel micrometers, so 955 times 1 divided by 1 times 10 to the 6th, that is going to equal 9.55 times 10 to the negative 4 meters. Now that I'm in meters, I feel a lot more comfortable taking this formula where again I am solving for frequency equals, and then I can take the speed of light, which I know is on our reference table, and that is 2.998 times 10 to the 8th meters per 1 second divided by our wavelength, which is 9.55 times 10 to the negative 4th meters. And the important thing to realize here is that meters cancels meters, but this per second, that means seconds is going to be on the bottom, which is actually what I want because I know that frequency is either measured in per second or hertz. So when I work this out, my final answer should be 3.14 times 10 to the 11th per second. Or another way of saying it is cycles per second. Let's do another example. Calculate the wavelength in nanometers of radiation that has a frequency of 5.50 times 10 to the 14 cycles per second. So again, we're going to start off by writing out our formula that's found in the reference table. Speed of light is equal to frequency times wavelength. This time I'm solving for wavelength, so I'm going to manipulate my formula around. So its wavelength is equal to speed of light over frequency. So now I'm going to plug in the values that I have. I know that the speed of light is 2.998 times 10 to the 8th meters per second, and that my frequency is 5.50 times 10 to the 14 cycles per second. And when I work this out, I can see that seconds are going to cancel seconds, and I'm left with meters. And that's all well and good, but there's only one tiny little problem. And the problem is that frequency, wavelength, is not measured in meters. Instead, it is measured in nanometers. So I have to take this value that I get, and I have to convert it over into nanometers. So if I work out this part, it's 5.45 times 10 to the negative 7 meters. And then I'm going to take it one step farther. And I know that in 1 meter, there is 1 times 10 to the 9th nanometers equals, and then I know that I've set this up correctly because meters cancel meters. And when I work this out, my final answer in nanometers will be 545 nanometers as my final answer. Let's do some more practice. Calculate the distance traveled by electromagnetic radiation in 50 microseconds. Okay, in order to do this, I need to take the time in seconds and multiply it by the velocity, which will be in meters over seconds, otherwise known as our speed of light, and that will give us our distance in meters. The velocity is in meters per second. I'm in microseconds. So like I've done before, I'm going to say, all right, I have 50 microseconds, and I know that's 1 times 10 to the 6th microsecond in every 1 second. So if I work this out to 3 significant figures, that's going to be 5.00 times 10 to the negative 5 seconds. Then I'm going to take this value and I'm going to substitute it into my formula. So 5.00 times 10 to the negative 5 seconds times the velocity, which is just the speed of light, 2.998 times 10 to the 8th meters per second. And when I work this out, I'm going to get 1.50 times 10 to the 4th meters, because my second over second canceled and I'm left in the units of meters, which means I've calculated the distance. Excited mercury atoms emit, which we know means release, light strongly at a wavelength of 436 nanometers. Calculate the frequency of this radiation. So I'm going to go back to use my formula. C equals frequency times wavelength. I'm going to rearrange this so I'm solving for frequency. So frequency is equal to speed of light over wavelength. And as I have done before, this 436 nanometers, I need this in meters. So 436 nanometers, multiplication sign in a line, 1 times 10 to the 9th nanometers in 1 meter. And nanometers cancel nanometers, so I'm left with the unit of meters, which is what I want. And this will be 4.36 times 10 to the negative 7 meters. So I'm going to take this and I'm solving for frequency. Speed of light is 2.998 times 10 to the 8th meters per second over 4.36 times 10 to the negative 7 meters. Meters cancel meters. I'm left with cycles per second. And when I work this all out, I get 6.88 times 10 to the 14th cycles per second. What is the color associated with this wavelength? Now you might say, what do you mean? What wavelength are you talking about? Well, the wavelength in the previous question, of course, and that wavelength was 436 nanometers. Now, in order to figure this out, you need to have some reference point to look at. So here is our electromagnetic spectrum below. So 436, well, 400 is right there. And each one of these marks is going by 20 nanometers. So 436 nanometers, probably, I don't know, somewhere around that. So the color that we would associate with this wavelength would be violet. So what did you learn? We talked about the wave nature of light. We talked about the difference between amplitude, wavelength, and frequency. And then we did some example problems at the end involving speed of light, frequency, and wavelength. Need more help? Feel free to contact me. Have a great day.